Hi Austin, this is the concept review video that I'm making for you that we talked about. I'm going to cover lesson 1. I'm going to go through the problem set. Well, I already did this. I'm going through the problem set. I'm looking for creepy math words that might be hanging you up. This is the list I came up with. Some will just require a quick definition. Others, I'll give you some background information that might make your job a little bit easier. But let's brush some of these cobwebs away and get you going on your math for the year. Okay, the first concept is the idea of complement The first one is complementary angles. And the idea with this is that you have two angles, and they could be lots of different angles. This is just the picture I'm drawing. We're going to call this angle A, and we're going to call this angle B. And if we take the degree measurement of those two angles, they add up to 90 degrees. So we can say A is the complement of angle B, and we can say B is the complement of angle A. That's just two different ways of saying together they add up to 90 degrees. So if angles are complements, they add to 90. And just so you don't die of boredom while I'm doing this, I recommend you take notes and write down all the stuff that I'm talking about. Supplementary angles are the same idea, except they add to 180. Okay? Again, the language, we can say that C and D are supplementary angles, or we can say that C is the supplement of D and D is the supplement of A. Okay? So sometimes we abbreviate those words. All right? So that's all that means. Okay. That's geometry. Let's switch gears. Let's go into algebra. I think I want to go, well, I'll just do this. Rules for exponents. There's a handful of problems in this homework lesson, exponents. There's a handful of problems in this lesson that require you to know the rules for exponents. So even though you didn't specifically ask, I'm just going to blow through these. I mean plus, because I love them. Ready? So we've got 3 rules for exponents. And we're going to draw a chart. The 3 rules, I'm going to put the names of them here, and then I'm going to show you how they work over here. This chart, if you've been with me through Algebra 1 and 2, or either of those, I draw this chart a million times. I love it. But it's super helpful for these kinds of problems. The first rule is called the product rule, and that's what we use when we've got 2 bases, each one has an exponent, and we're multiplying them together. Product taken from the fact that we're multiplying these. To combine the exponents, we add them. That's a plus sign. Right? Okay, next rule, quotient rule. This is the rule we use when we're dividing one base with an exponent over, it's got to be the same base. That's why I'm using x's for both of these. The bases have to match. The exponents don't have to match. That's why I use m and n. Don't ask me why. Those are just the letters we use. But in this case, we subtract numerator minus denominator. That's the quotient rule. The third one is the power rule. And this is the rule we use when we've got a base with an exponent on it and we're raising it to a higher power. Thus the name, the quotient rule. The power rule. Quotient implies dividing. Power I can't talk. Power rule implies we're raising one power to a higher power. This is where we multiply. That's a dot for multiplication. The common mistake that gets made is that people want to multiply the exponents when we're multiplying the bases. Multiplying and multiplying doesn't go together. That's how my brain remembers it. I also remember, okay, multiplying, dividing, raising to a power. That's kind of the way most of us are taught. That goes from easier to harder. And then plus, minus, multiply. That also, depending on how we were taught, that often feels like easier to harder. So those are the ways I help to memorize. If you can recreate this chart, either on a piece of paper or in your brain, it's going to help you a lot with a bunch of these problems. Okay. Look, we already filled up one page. The next pair of terms are both part of what we call systems of equations. Systems of equations are when we have, I'm going to choose an actual example from the book. Copying. You copy too. Okay, so the dead giveaway that this is a system of equations, is that parenthesis. That's the big tip-off. Whenever we see one of those pointy, brackety deals, we know we have a system of equations. The other tip-off is that this is a system of two equations, so we notice we have two variables that show up in both of the equations. Oh, that means we can use the two equations to solve for both of the variables. A general rule of thumb is that however many variables you're trying to solve for, you have to have that many equations in order to do it. So two different variables, two equations, we're good. There are different ways of solving this. The first one we learned was substitution. When we solve by substitution, what we do is we set one of the equations so that one variable is on the side by itself and the stuff is pushed to the other side. So let's fix this one. We're going to take the first equation and we're going to subtract n sub d to the other side. And we don't let those subscripted variables freak us out. This problem is a coin problem, so it's number of nickels plus number of dimes. That's what that stands for, clearly. So we just shove one of the variables. It doesn't matter which. We can do it either way. We shove one to the other side so that this is by itself. This is the magic. Then we take this and substitute it into the other part of the equation. So now, instead of saying number of nickels, we're going to say that, and then we're going to carry on with the rest of the equation. So we rearranged this, and we took this and plugged it in to the same spot in the other equation. 5 times the number of nickels, which is this, plus 10. And then we can solve from there. I'll go ahead and solve it. So 250 minus 5nd plus 10nd equals 450. All right, I'm going to combine those like terms. I'm going to swim that 250 over. Yes, it's a fish. This comes to 5nd. That's gone. This equals 200. Yeah, baby, the number of dimes equals 40. And then we can quickly see, I don't even have to do any math. I can do this in my head. The number of nickels is equal 50 minus 40, which is 10. Okay? So that's how we can solve this problem by substitution. The second way is by elimination. And in this, we take a slightly different strategy. what we do is we look down the columns of the variables and comparing like with like, right? These are set up, I didn't write them so they're right overhead, but we can compare the number of nickels and the number of dimes. And we decide which one we want to eliminate. I'm going to copy it. It'll be easier to explain. NN plus ND equals 50. And I can make my columns really crisp. And what we do is we try to figure out a way to eliminate one or the other of the variables. I'm going to choose to try to eliminate the NDs because I'd rather multiply by 10 than 5. I mean, that's pretty picky, but... So what I'm going to do is I'm going to multiply this whole equation by minus 10. When I do that, this will become minus 10 ND. These two will cancel, and I will be left with an eliminated ND, and I'll just have one term left. So let's go ahead and multiply. I'm going to write that down here. So it'll be minus 10 times the number of nickels plus, and I'm just going to write it like that. That's kind of weird. Minus 10 number of dimes, right? Because I have a minus sign there, equals minus 500. Okay, I'm squiggling this out because I don't want to look at that anymore. I've rewritten that one down here. Minus 5 times the number of nickels, that's canceled, equals minus 50. Oh, divide by both sides. Divide both sides by minus 5, and I get the number of nickels. I'll squeeze it in here. Number of nickels equals 10. I'm sorry, I said nickels. I meant nickels. This shouldn't be a D. Didn't know if I should believe my hand or my mouth. Number of nickels is 10. Look, that's the very same answer we got there. And we could plug that into one of the original equations and solve for the number of dimes, but I don't want to take the time to do that. So elimination and substitution are two systems of equations. The third one that we've already learned is graphing. Graphing is a visually appealing but mathematically annoying way to solve a system of equations. What you do is you graph them. There's our basic Cartesian coordinate system. This picture, these are the two lines. I've graphed them independently. It looks really cool to say, oh, look, there's the intersection of the two lines. That's the point that serves as our solution. What's annoying is that it's really hard then to nail down what exactly are the numbers at that point, because you're just looking at a graph and trying to estimate, and unless it's very specifically landing on the corners of the graph paper, then you're just kind of guessing. Okay, so we're going to learn number 4 and number 5, two more methods of solving systems of equations this year. So, spoilers, it's going to be fun. Okay, moving on. Congruent line segments, another geometry, congruent, another geometry phrase. Geometry just seems to me to have the most kooky language. Okay, there's a line segment, and I'm telling you that's a congruent line segment. Congruent is geometry for equal. It kind of makes sense because we're not talking about the lengths of these segments specifically. We're not saying this is 4.5 centimeters and the lengths are equal. We're saying that the segments themselves are the same length, but we say congruent instead of equal. Done. Okay, sizes of angles. You'll remember this. This is called a right angle. It's common, it's useful, it's got a 90 degree, and this is the symbol for 90 degrees pitch to it. What if you make the angle tighter? What if you make it looser? We call this acute, and we call this obtuse. I'm talking about the angles here. We can apply this to triangles by creating a triangle that has at least one of these angles, right? So we could connect the dots, and then we would be talking about triangle sizes, all right? This, though, remember, is measuring the size of the angle. Okay, done. Let's talk about circles. Angles in circles. All right. There's two basic variety that I want to discuss right now. There's the middle of the circle. If we have an angle of any size that comes out from the center, that's called a central angle. And if the measure of the central angle is x degrees, then it's going to be the same size as this, what we call the intercepted angle. All right, so those are the same. If we have this is the Teenage Mutant Ninja Turtle style angle, because doesn't that look like this, the profile of a ninja? His eyes here and his, it would be tied back here. It's a profile. I always think of that. This is called an inscribed angle. Inscribed means written within, and that's the idea, is that the angle is written within the edge of the circle. I mean, that's kind of weird, but okay. The thing we remember about these is that the size of the angle still has a relationship to the length of this intercepted arc, but the intercepted arc is twice as big. That's a degree sign. It looks like an O. The intercepted arc is twice as big as this, okay? So when you're measuring them, that's handy to know. Oh, I skipped a couple things on my list. Going out of order, you won't care too much, I hope. Equilateral triangle is one where all the sides are the same. And if all the sides are the same length, right, equal side. If the sides are all the same length, remember those tick marks show us that they're all the same, then the angles are all going to be the same too, right? So it's equiangular as well. Now, I think it's in the same problem. They talk about altitude. The altitude of a triangle might be one of the sides, but it might not be. The altitude is the height. And you know, I talk about this with my little Spidey friend because it helps me really visualize this. So we look at our three different kinds of triangles. There's a right triangle. Here's an acute triangle. All the angles are less than 90 degrees. And here's a obtuse bad boy. Now, the altitude in these triangles is going to be found in a different place. And what we do, again, is we send the spider up to the highest point and ask it to drop a line down. That gives us the altitude of the triangle, or the height. So in a right triangle, yeah, it's the side. But in this triangle, the altitude is not one of the sides. And by the way, our spider always drops perfectly perpendicular lines. He's cool like that. For this one, the highest point is here. Remember this? And we measure the altitude or height. We have to go outside of the triangle. Sometimes John shows that dotty line. But altitude, the altitude of a triangle is found in different places depending on the basic shape of the triangle. Interesting. All right, sectors. What is a sector? We're going back to our circles now. A sector of a circle is the area that is formed within a central angle. It is the slice of pizza. And what I mean by that is that it includes the crust, if you will. Sometimes we'll look at shapes in circles that are like this. They take a sector, but then they cut the crust off. Okay? That's something different. That's not the same as this. This is a sector. It includes the crust. Okay? Let's go back to a circle and just cover the basics. You know that that's the center. That's the radius. If we take two radii and put them in a straight line, so it goes from edge to center and center to edge, pretend that's perfect. We call that the diameter. Okay? Radius is just from center to edge. Diameter is edge to center and then straight through to the other side. Pretend that's perfect. It's so not. All right. If a line runs along a circle but only touches it at one point. Oh, heaven help me, it's hard to draw. Pretend it's touching at just one point. We call this line a tangent to the circle. Okay, you can also have tangent circles. So for example, and this is in the problem, there's a picture that looks like this. I'm going to have a hard time drawing this perfectly. The circle, the picture looks like this. It's a box with 9 circles inside, a 3 by 3 array of them. Oh, it's so not perfect. Please imagine with me. This is problem 28. It says, in the figure below, all adjacent circles, adjacent means next to each other, are tangent to each other. What they mean by that is that all the circles are touching by just one point. So they're right up against each other, not overlapping, but there's no gap space in between them either. Okay, so those are the single points that show them touching. And the outer circles are tangent to the square. Now, my picture is sadly lacking in this respect. But again, pretend it's perfect. So what they're saying is that everything just touches the edges of everything else. There's no extra space in there. And so I'll give you a hint. The sum of the areas of the 9 circles. Okay, the area of a triangle is pi r squared. R is the radius. You know that. You also know the circumference is, you can say it so many different ways. Pi 2r. This has an exponent, this it doesn't. If you were trying to find the radius of these circles, imagine this, if you will. If you hooked up all of those radii, that would give you this dimension of the square, right? So let's just say this radius was 2. It would be 2, 4, 6, 8, 10, 12. The length of the square would be 12. And then the same way going down. Because these are all tangents to each other, there's no extra space. 2, 4, 6, 8, 10, 12. If 2 is our radius, it would be a 12-inch square, right? 1, 2, 3, 4, 5, 6. 6 radii, they're each 2 inches. I'm making that up. So this would be, I'll put it down here because there's more room. This would be 12 inches as well, all right? That's a great hint on how to get going on problem 28. Last thing I want to say is that in this book, John is trying to help students of yesteryear prepare for the SAT. And back in the day, when was this book written? The 90s, maybe? The SAT had a certain type of problem that are referred to as concept review problems. Here, I'll show you. So at the end of a lot of these lessons, John is giving you a chance to practice these SAT problems. But, spoilers, the SAT doesn't use problems like this anymore. Thank heavens, they're really tricky. So you don't have to practice these. There's no need to do that. It was only for SAT prep, and you don't need to do that. So we do not do the concept review problems. We do all the others, all right? In these first couple lessons, you'll notice, just let me find my paper. You'll notice that I gave 2 days of the week for doing both lessons. If you've watched the video, you know I wanted you to do the odds one day and the evens one day, or like 1 through 14 one day and 15 through 30 the next. For the first 4 lessons, I want you to do all the problems, and then we can get back to our rhythm of doing just the odds. So that's what my thinking is here. That's why I doubled up on those numbers. Be sure you watch the videos. It will help you a lot prepare for diving back into this. Okay, if you have any questions, Austin, feel free to reach out to me. If you see any other words, creepy math words or concepts that you don't immediately remember what they mean, just text me and I will remind you. Okay, thank you. I will talk to you soon. Farewell.